Chapter 12. We're going to be looking at some vectored value functions now. Starting off with our first section, which kind of just introduces you to the idea of what a vector valued function is. So, in Cal 2, you learned about parametric equations, right? And how basically you have an equation for x in terms of t, an equation for y in terms of t. Here you've even seen equations for z in terms of t. Vector valued functions are literally the exact same thing. They're just a different notation for it. So rather than saying we have an equation for x, y, and z, we just write our function as a vector whose components would be the parametric equations. So to illustrate this idea, let's look at that first example. Represent the parabola given by that equation using a vector valued function in 2 dimensions. So first what I'm going to do is write out what I would put for parametric equations, right? Easiest way to do this would be to let one of these variables be t, easiest to let x be t. And then y is just t squared plus 1 because x is t. So writing our function out as parametric equations would look like that. To write this as a vector valued function, I would write a vector and I can write it in component form like this, or I can use my unit vectors I and j. But this is what my vector valued function looks like. And typically when you see something like this, the function might be called r of t, right? Where r is a vector. So there you go. You see, they really are the exact same thing. Professor Cordelia getting restless at night. Okay. So the next example, let's say that we want to convert the vector valued function given here to an equation in terms of x and y only, and then sketch a graph. So remember, if we have a vector valued function, we can always write each of the components, yep, as parametric equations. So if I look where my I is, right, that's going to be the equation for x. So x would be 2 cosine of t, right? And then for y, we would get y is equal to -3 sine of t. Okay. So keeping this in mind, here's the idea. We're typically going to try to solve for t, right? And then use the fact that both of these things are equal to t to set them equal to each other, or thus getting us an equation, right? So my first step, if I wanted to solve this equation for t, would be to divide by 2. So I get cosine of t equals x over 2. For the equation for y, I could divide both sides by -3. So I get that sine of t is equal to -y over 3. Here's the thing though. I could solve both of these for t. First one by taking arc cosine of both sides. Second one by taking arc sine of both sides. And I would get an equation. It would be a gross one. But the way that the textbook does this particular example, they actually use the trig identity to make it a lot nicer looking. And in reality, you could choose either approach to do this. Um, like I said, though, generally, most of the time, you're solving both equations for t and then setting them equal to each other. And that's what you would do. All right, for this one though, there's an opportunity here to use some trig identities. So I know that sine squared t plus cosine squared t is equal to 1. I also know that I can express sine squared t as negative y over 3 squared. And I can express cosine squared of t as x over 2 squared. So to make this an equation that I will definitely be able to kind of recognize because I do have to graph this one, I'm going to rewrite that. So sine squared t plus cosine squared t gives me 1. And then if I square this, I get y squared over 9. Notice that's positive because we squared, plus x squared over 4. And this is my equation after eliminating the parameter, right? And generally, like I said, what you do is you solve both equations for t, set them equal, that's an equation. In this one, though, we needed something that we would be able to graph, so I used this trig identity as a way to kind of make it prettier. You also could have solved for t and rearranged it to get this form. Would have been a bit more involved than just doing this, though. So to sketch the graph, first thing I notice is that both of these are positive, both terms are squared, we're equal to 1, so that's an ellipse. Specifically, it's an ellipse where the radius in the x direction is 2 and the radius in the y direction is 3. And we're centered at the origin because there are no horizontal shifts or vertical shifts with the x or the y. So drawing this out, that's my x, that's my y. Okay, we get a radius of 3 on the y-axis. So I'll go up 3, I'll go down 3. That'll be the top and the bottom of the ellipse. And then 2 units out on the x-axis, both directions. That'll be the right and the left side of the ellipse. So that's going to make our little oval shape. And there we go. Other thing to note, when you graph functions that are either given in terms of parametric equations or are given as vector valued functions, there's a direction associated with it. So yes, this is the pathway, but to have a complete graph for this, I have to also figure out where my starting point is, where my stopping point is, and generally which direction we're moving. To figure that out, let's look at this restriction that they gave us. T is between 0 and 2 pi. I'm going to start by plugging in 0 for t for each of these components. Right? If I can use either, yeah, I can use either the vector components or I can use the parametric equations. It doesn't matter. If I plug 0 in for t, I get an x coordinate of 2 times cosine of 0. Cosine of 0 is 1. So that would give us an x coordinate of 2, meaning that we're starting right here on the right side of the ellipse. If I were to go to another coordinate, right, and I can pick unit circle coordinates. Oh, whoops, forgot something here. And then for y, of course, if you plug 0 in for t, sine of 0 is 0. So we get a y coordinate of 0, which again puts us right here. Okay, so if I want to find the direction that we're moving, I can pick a value that logically would make sense that would also be easy to plot. So I could pick unit circle values. For cosine, I know that I get a nice neat number um, when t is pi over 3. So we could do that. I also know that I could get a nice clean y value if we did pi over 6. I could do that. I could also just go to a quadrantal. That would be pretty easy. All right, so why don't we do that? Just go to pi over 2. So if I plug pi over 2 in for t in the x equation, we get x is equal to 2 multiplied by cosine of pi over 2. That gives me 0. And for the y equation, we get negative 3 times sine of pi over 2, which gives me negative 3. Sine of pi over 2 is 1. Multiply, you get negative 3. So essentially we get to this coordinate next, meaning that we're starting here, we're going this direction. And if I were to plug in pi, I would end up getting -2 for my x coordinate and 0 for my y coordinate. So from here, we end up here. For 3 pi over 2, the next logical step, 3 pi over 2, x would be 0. The y coordinate would be +3. And finally, if 2 pi, we would end up right where we started, since 2 pi is coterminal with 0. So essentially, we have this ellipse, and we're traveling clockwise around the ellipse, starting at the right side. And it's exactly 1 revolution. There we go. That's it. Next example, we want to express this vector valued function with this restriction as an equation in terms of x, y, and z, and then sketch the graph. So again, we can start off with our parametric equations. We get x is equal to 4 cosine t. We get y is equal to 4 sine of t. And then we get z is equal to t. All right. So we can take the same approach, right? Generally, the idea is that we're trying to solve each equation for t, and then we can set them equal to each other. Thing about it, though, is this also involves a sine and a cosine. So if I wanted to, I could actually take the exact same approach that I did in this last example, where I isolate the sine and the cosine, and then I use that trig identity to make my equation prettier, which would be helpful since I need to graph this one. So if I do that, I get cosine of t is equal to x over 4. I get sine of t is equal to y over 4. And then I don't need to do anything with the z equation because that's just t. So again, if I combine these, I end up getting cosine squared t plus sine squared t is equal to x over 4 squared plus y over 4 squared. We know that this is going to be 1. We know that this is going to work out to x squared over 16 plus y squared over 16. Now, the thing I want you to notice about this one is that the numbers in the denominator are the same, which means this is not going to be an ellipse, it's going to be a circle. To make it a little clearer, if I were to just multiply every term by 16, or if I never divided by 4 in the first place, I would have gotten the same idea, the same conclusion, right? Namely that we have a circle centered at the origin with a radius of 4. Here's the thing though, that's not quite it, because we still have this z that we're worrying about, right? It didn't end up factoring in here because z was just equal to t. And when we eliminate the parameter because they're equal, we eliminate the z. So the equation that we get doesn't depend on z, but it is still a three-dimensional surface. All right. So if you remember from the last section, or 2 sections ago now, 11.6, what does that graph look like? Hopefully you said it's a cylinder, because you would be right. So if I were to graph this, I'd have my x, my y, and my z. Remember, the floor is going to be that circle that we talked about with a radius of 4. So we're going to go out 4 units. Try and put both perspective and a nice circle. Yeah, close enough. All right, so this is 4. This is 4. right? And this kind of forms the base, if you will, of our cylinder. It's not really a base because it goes infinitely in both directions along the z-axis, but it's a way for us to start. So if I draw the rest of my cylinder, all right, we're going to end up with something that looks, I probably shouldn't have drawn that one there. Messy, messy. Yeah. So we end up getting this cylinder. Yep. There we go. That's the drawing, that's the graph, that's the equation. All right, two more examples to go, right? So now that we've looked at what graphing vector valued functions looks like, we can kind of shift a little bit to look at limits. And one thing I'll say about all the different calculus stuff that we do with vector valued functions is that it's the exact same stuff that you've already learned. You're just doing it separately for each component, right? So if I want to find the limit of a vector valued function, I literally just need to find the limit of the x part, the limit of the y part, and the limit of the z part and put it all together. That's it. All right, so for this example, we have r of t as a vector valued function. These are our components. A is a constant, so it's just a number like 5 or 3.1415 stuff that I'm not going to get into because then I'm going to break into song. We want to know the limit as t approaches 0 of this vector valued function. Okay, so let's start off by writing that out. So this is essentially just going to be the limit as t approaches 0 of t I plus the limit as t approaches 0 of a j plus the limit as t approaches 0 of a squared minus t squared k. And if I take these limits separately, they're all pretty straightforward, right? As t approaches 0, this approaches 0. A is a number, right? So it doesn't depend on t. So as t approaches 0, a is just going to stay a. And lastly, as t approaches 0, a squared minus t squared is going to approach a squared. Since we don't typically write zeros, we can express this as aj plus a squared k. And that would be the limit of that vector valued function. The next part asks us to figure out what r of 0 is. So remember, limit is what the value approaches as your variable, or in this case, your parameter, approaches a certain number. This is what I get exactly when the parameter is equal to that number. Remember that those are different. Yes, in this case, we were able to kind of just plug the number 0 in for t, but remember, at their core, a limit is not the same as an equality, right? Limit means approaching. Equality means exactly at, exactly equal to. So for this one, I'm literally just plugging 0 in anywhere that I see t. So 0i plus aj plus a squared minus 0 squared k. Remember, we don't write the zeros, so this ends up just being aj plus a squared k. Okay, now what do we notice about the limit and r of 0? You should notice that they are exactly the same in this case. Remember, that's not always true. but in this case it is. And when this is true, so when we know that this limit exists, meaning the left and the right side agree are the same number, and it's equal to what we get from plugging 0 in for t, we would say that this function is continuous when t is equal to z. So we would say since the limit as t approaches 0 of r of t is equal to r of 0, r of t is continuous at the point when t is equal to 0. Next example, we want to determine the intervals on which our vector valued function r of t is continuous. So I'm not sure how your pre-cal, Cal 1, Cal 2 professors kind of talked about this idea. But when we want to assess continuity over an interval, right, that's different from when we want to assess at a point. If I want to assess continuity at a point, I just look at the limit, I look at the actual value, and if they match, then the function's continuous there. But over an interval, the process is different. I have to look at each of these components and I have to figure out, is there anything that I am not mathematically allowed to plug in for t? Right? So I like to call them math no-nos. We look for math no-nos. So looking at each separate component for t, I can plug anything in for t and I get that number I. That's fine. There's nothing there's nothing that I can do that would be a math no-no there. For k, same thing. If I plug in any number for t, I'm guaranteed to get something out as my k component that is a real number. Foreshadowing. Look at j though. This involves the square root. Anytime that we have an even root, you have to remember that the inside of that root has to be positive or 0. Basically, it has to be non-negative. So we know that our limit for this function will only exist for values of t where this is not problematic. So because of that, I'm going to take t plus 1. I know that this has to be greater than or equal to 0. I know that that's going to be true if t is greater than or equal to -1. Since there are no restrictions on my x component or my z component, this is the only one that has issues. This would be the answer that we're looking for. So we know that r of t is going to be continuous for any value of t that is greater than or equal to -1. And there we go. Easy peasy. So kind of giving you a recap there. We started off by talking about what vector valued functions are. They're basically the exact same thing as parametrics. The only difference is that we use vector notation to write them. Right, then we did an example where we graphed a two-dimensional curve and a three-dimensional surface after converting our vector valued function into just a function of x and y. Then we talked about limits of vector valued functions. And the main idea there was that if you take the limit of a vector valued function, you could take the limit of each component separately. And if one of them fails, then the whole thing fails. So if the limit does not exist for one component or more, then the limit does not exist for the entire vector valued function at that point, or as t approaches that point. Then I just briefly discussed math no-nos and how we can use them to determine whether a function is continuous on an interval. And that's pretty much it. Happy mathing.